This is continuation of our discussion on power series functions. So far, we have defined what are power series functions and how to find its domain. For example, we can use Cauchy root test, Cauchy-Hardeman root test, and ratio test to find the domain of these power series functions. Now we are interested in some other properties, for example, differentiation and integration of these power series functions. Now, for the current time, we are interested in the differentiation, and the integration topic will be touched in our far future discussions. Now, let's begin with the differentiation part. Let's recall ourselves what is a power series function. It is basically infinite series Cn z minus alpha raised to power n, where n varies from 0 to infinity. Over here, alpha and C0, C1, C2 up to so on, these are all fixed complex numbers, and z is basically the variable that makes this expression into a function. Now, as I have said, that there are many ways for finding the domain of this function, and we can also find the radius of convergence. So over here we can see this blue disk is basically the domain of this power series function. Okay, and since it is basically a disk with radius rho, so that's why we call rho to be the radius of convergence. So if we take any point inside this disk, then for those complex numbers this series converges, and that's why we call that it is the domain. And outside this disk we have complex numbers for which this infinite series diverges, and that's why they are not included in the domain. Now the question is, when can we differentiate the power series function? And most importantly, if we can differentiate, or if the derivative exists, then what is the derivative? Now we are going to focus on these questions for the rest of this module. We are going to begin with some notations that we will use for the rest of our discussion. So we denote by fk the kth derivative of f of z, and if k is equal to 0, then basically it means the function itself. And for example, if k is equal to 1, then it is the first derivative. If k is equal to 2, it is the second derivative, and up to so on. Now this is the main result of this current discussion, where we are given this power series function. Then there are three claims in this result. So the first claim is this function f of z is infinitely differentiable for all z in the domain. Okay, so basically rho is the radius of convergence, so that's why this is the domain of this power series function. And if this is infinitely differentiable, then the second part says how to find the derivative. The kth derivative can be written in the following form, and the third part says that we can in fact find the values of these ck's using the formula given here. So these are all three relevant questions if we want to calculate the derivative of a power series function. Okay, so the first part guarantees when does it exist, the second part calculates it, and the third part gives the values of this ck. Now we begin our proof with the second part. In other words, we want to prove the formula for the derivative of this complex valued function. Of course, in this case z belongs to the domain. Okay, so it basically belongs to this disk with radius rho and center alpha. Now there are two steps to prove this second part of the theorem. So in the first step, we prove the statement for k is equal to 1, and of course the second part can be proved using induction. Okay, so this is the most important part of our proof, because if we can prove this case, then for k is equal to 1 precisely, so for k is equal to 1, if the statement is true, then by induction we can prove this for the rest of the case. And if all of the derivatives exist, then the first part is very obvious, that the function is infinitely differentiable. And the third part can be obtained by taking z is equal to alpha in the formula for the kth derivative. So that's why the case of k is equal to 1 is the main theme of this theorem. Now let's prove this statement for k is equal to 1. Now we prove, we define this g of z, where n is equal to 1 to infinity, n cn z minus alpha raised to power n minus 1. Now, why we are defining g of z like this? Now, remember, f of z is given to be n is equal to 1 to infinity Cn z minus alpha raised to power n. And if assume that the function is differentiable and the derivative can be obtained by taking the term by term differentiation, then what is going to be the derivative if we differentiate each and every term? Obviously, this is going to be g of z. So that's why we want to prove that the derivative of function at some point z0 of the domain is going to be g of z0. So that's why we are taking this g of z, and we divide this f of z, the power series function, into two parts. So in the first part we have the first j plus 1 terms starting from n is equal to 0 to j, and in the second part we have the rest of the terms, in other words starting from j plus 1 to infinity. Now this Sj can be considered as the j plus first partial sum of the series, and of course if j approaches to infinity, then this Sjz is nothing but f of z, and this Rj is basically the rest of the terms. Now the most important observation about this Sj is that it is a polynomial, because there are finitely many terms in Sj, and we are going to use this fact in our proof. Now the radius of convergence of this g of z that we just defined can be found to be rho. Now why it is true? Now we are going to use this D'Alembert's ratio test to find the radius of convergence of g of z. Now remember, what is the radius of convergence of our given power series function f of z? Well, that is rho, and we can say that rho is equal to 1 over limit n approaches to infinity and the mod of Cn plus 1 over Cn. Okay, now given this thing, we are going to apply this ratio test to get the radius of convergence of this g of z. Now let's apply this ratio test. Over here, what is the n plus 1 term? Of course, by taking n to be n plus 1, so n plus 1 Cn plus 1. Okay, so over here, by just replacing n with n plus 1, we get the numerator, and by taking n to be n, it is nCn. Okay, now we can divide this limit into the product of two terms, n approaches to infinity n plus 1 over n, and n approaches to infinity Cn plus 1 over Cn. Now we know something about this thing, this limit. Of course, this is just 1 over rho. Okay, so and this limit can be written in the following form: n approaches to infinity 1 plus 1 over n. Now when n approaches to infinity, this term approaches to 0 and we are left with only 1, and as we have discussed, that this is nothing but 1 over rho. So we get the following thing, 1 over rho. So that's why we can say that the radius of convergence of g of z is the same as the radius of convergence of f of z, which is rho. Now moving on with the case of k is equal to 1, what do we want to prove? As I've said earlier, that we want to prove, so we defined g of z so that we should prove the following thing, that f prime z0 is equal to g of z0, where z0 is any point in the domain of this function. Now if we want to prove that the derivative of this function at point z0 is equal to g of z0, then we want to show that, in other words, we want to show that the following limit z approaches to z0, f of z minus f of z0 over z minus z0 is equal to g of z0, because this is just the definition, of derivative. Okay, now over here we are calculating this limit. Okay, so what does it mean then? So let's recall what is the definition of the limit. So the limit z approaches to z0 of f of z is L if for every epsilon there exists delta, such that the distance between f of z and L is less than epsilon whenever the distance between z and z0 is less than delta. So the functional values are getting closer and closer to L, and they are as close as we want to this number L. Now in this case, the function is basically replaced with the expression f of z minus f of z0 over z minus z0, and L is replaced with g of z0. So the expression becomes, for every epsilon there exists delta, such that this is less than epsilon whenever z minus z0 modulus is less than delta. And of course, we are not allowed to go outside the domain of the definition of the function f of z. So that's why the next condition is very important, that z always belongs to the domain. Okay, so let's move on. And if z is any point in the domain, then of course z cannot be at the boundary because it is a disk. So there must be some number r such that z0 belongs to that inside disk. Okay, so if z0 is not at the boundary, then it will be inside the boundary, and we can always find some distance between the boundary and that point. So there will be some another, for example, circle in between z0 and this boundary. So that's why we can find this r such that z0 belongs to this disk with radius r, and center is the same, alpha. Okay, so what do we need to find now? We need to find, of course, given epsilon is arbitrary, we need to find a delta such that whenever z belongs to this disk, or whenever z belongs to the disk with basically this should be z0, so center z0 and radius delta, which is of course contained inside this dr alpha, which is contained in d rho alpha, the bigger disk. Okay, so we need to find this delta such that this inclusions are satisfied. Okay, so let me remind you again, given epsilon we want to find delta. Okay, so the function is f of z minus f of z0 over z minus z0, and the limit is g of z0. Okay, and of course during the course of our proof there will be other conditions imposed on j and the variable z. Okay, now let's begin with this expression. Okay, so this expression, by using the fact that f of z is equal to sjz plus rjz, we can write down this expression in the following form. So f of z is sjz plus rjz, and of course f of z0 is basically sjz0 plus rjz0, and g of z0 remains the same. So we can divide these terms in the following form: sjz minus sjz0 over z minus z0, and rjz minus rjz0 over z minus z0, and g of z0 remains the same. And moving on, we can add and subtract sj prime z0, and just writing the terms, reordering the terms in the following way, we get the following expression. So this is basically this term and the term that we added and subtracted, and this term goes to here, and g of z0 comes here, and sj prime z0, which we added and subtracted, comes here. So there are three parts or three components of this expression. Okay, now in our further discussion we want to concentrate on each of these three parts. Okay, so we want to show that, remember, we want to show that this expression is less than epsilon, and we want to find some delta such that whenever the distance between z and z0 is less than delta, then this expression is less than epsilon. So that is our aim. Now we can use, for example, this triangular like inequality, that this expression is less than or equal to this term, and this term. We just divided the modulus. Okay, so nothing complicated here. Now moving on, as I've told you that there are three components, so let's call it mod b, mod c, and mod d. Okay, now we want to concentrate on each and every part separately. In other words, if I want to show that this expression is less than epsilon, then I want to show that this is less than epsilon by 3, this is less than by epsilon by 3, and this is less than epsilon by 3, so that when we add them together, then we get epsilon. So that is our aim. We will focus on each and every term, and we want to show that each term is less than epsilon by 3. Okay, so let's begin with the third part, the modulus d. So this is equal to rjz minus rjz0 over z minus z0. Okay, now using the value of rjz, we can write down rjz as this, and of course rjz0 like this. We are just using the definition of rjz. Okay, so moving on, we can write down these two summations in one summation. Okay, So once again, nothing complicated here. We just wrote these two summations in one summation, and this is less than or equal to, since it converges, so that's why we can write it down as less than or equal to Cn. Okay, so Cn is common, so that's why we can write down the modulus of Cn like this, and z minus z naught comes over here, and z minus alpha raised to power n and z naught minus alpha raised to power n comes over here. So this converges, so that's why we can use this property, and we can basically shift this modulus inside the series, and we will get less than or equal to sign. Okay, so now we want to focus on this expression. Okay, so let's focus on this expression, and let's try to show that this is less than n r raised to power n minus 1. And remember, what is r? So r is the basically distance such that z naught belongs to dr alpha. Okay, now this holds. We are not going into the exact details of this fact, but we are just going to give some hints of this thing. Okay, so if p and q are any complex numbers, then p raised to power n minus q raised to power n divided by p minus q modulus is going to be equal to this expression. So over here we haven't done anything once again complicated, we just divided these two polynomials. Okay, and moving on, we just use the triangle inequality. So we divided the mod in each and every term, and if we take in particular p and q are any complex numbers, but if we take p to be z minus alpha and q to be z naught minus alpha, then what is p minus q? So p minus q is z minus z naught. Okay, so which is the denominator over here. And if p is equal to z minus alpha, then this is this term, and if q is equal to z naught minus alpha, then this is this term. Okay, and since z minus alpha modulus is less than r, and z naught minus alpha modulus is less than r, so that's why each and every term, okay, so this is less than r raised to power n minus 1. Okay, so this term is less than r raised to power n minus 1. Similarly, each and every term is less than r raised to power n minus 1, and there are n terms, so that's why we have this expression. Now moving on, we have calculated so far that modulus d is less than or equal to this, and using this, which we just proved, we get the following expression. Okay, so that's what we have achieved so far. The modulus of d is less than this expression. Now one thing that we have achieved is there is no variable z in here. Okay, now the question is this series converges or not? Okay, so it happens so that this series converges, and why it converges, let's apply, for example, the ratio test over here. The n plus 1 term is this, nth term is this, and we can calculate eta n plus 1 over eta n, which is equal to n approaches to infinity, and eta n plus 1 over eta n. Okay, so these are just simple calculations, and moving on, just divide this limit into the parts, and we get r into 1 over rho. Of course, this is equal to rho, and this is just 1, and so we get r into 1 over rho. And what do we get? This is less than 1. Why this is less than 1? Because r is less than rho, and that implies r over rho is less than 1. So if this is less than 1, then this converges. So that's what we obtained so far. So if this is less than this and this series converges, so that's why we can find some tail of the series, because this series converges, so some tail of the series will be less than epsilon by 3, because this is the terms of the series are becoming smaller and smaller. So we can find after some j. Okay, so for example, if there is an integer n1 such that whenever j is greater than n1, then the tail ender terms, the sum of the tail end terms is less than epsilon by 3. Okay, so that's why this expression is less than epsilon, and that is the aim. So that is the first aim that we have achieved, that this modulus d is less than epsilon by 3. Now what we have achieved so far, so we have achieved that this third term of this expression is less than epsilon by 3, of course, after some n1. So whenever j is greater than or equal to n1, then this expression is less than epsilon by 3. And in our next discussion, we will prove that this part is less than epsilon by 3, and then this part is less than epsilon by 3, and then it will show that if this expression is less than epsilon with some conditions on z and j, then this will show that the function is differentiable and f prime z naught is equal to g of z naught. Now we will continue the proof of this theorem in our next module.